Hi, I'm Cassiel.
Hello, I'm Tina.
Hi, I'm Timothy.
I'm Noah, and we are Team Capybara from the Quantum Software Development course. Our project was to implement the quantum Hadamard edge detection algorithm on large images. But before we break down what that actually means, let's get some background on quantum computing itself. Instead of using classical bits, quantum computers use qubits, which are the quantum analog of a classical bit. Just like a classical bit, qubits can be measured as a 0 or a 1 at a certain point in time. What makes them unique is that they can be measured as a superposition of 0 and 1 at the same time. This unique characteristic allows us to represent exponentially more states with qubits than if we were using the same amount of classical bits. For example, 3 qubits could store information that would require 512 classical bits. Let's revisit what the QHED algorithm is. Edge detection is an essential feature in image processing, allowing us to find the borders of objects within a given image. While classical edge detection works fine for smaller images, the larger pixel values of bigger images causes it to slow down. This is where quantum edge detection comes in. The time complexity of the classical edge detection algorithm is O of 2 to the n, while for the quantum edge detection algorithm, it is O of n. This is an exponential speedup, but how does it actually do this?
First, we need to encode our color intensities and pixel locations into a quantum form. Since qubits are measured in ones and zeros, we can use a group of qubits or a register to represent a binary index. When a register of qubits are in superposition, they are in all their states, meaning they also represent all the possible binary combinations and all pixel indices. For example, in the image, we use 2 qubits in superposition to represent 4 pixels. Each state also has a corresponding amplitude or probability of being measured. By applying quantum rotation gates to each state, we can manipulate the amplitude to encode color intensity. Now, instead of having a classical array of n indices, we've encoded the entire image into a length log 2n register.
This is the Hadamard gate, a very powerful tool used in many different quantum algorithms. Applying it on a qubit, we can obtain the following transformations. Take note of the sign flow. Another property this algorithm takes advantage of is the alternating zeroth qubit, which makes sense if we consider how the purity or the even/oddness of a number always changes as we add 1 to it. Now let's denote the array of indices as I, and applying H0, so Hadamards on qubit 0, quickly we can see a pattern emerge as we apply it on successive indices. Mathematically, the Hadamard gate can be represented as a matrix. Applying it on a QPi thus gives the following. We can see the same pattern emerge in the result. Now we have access to adjacent differences, but looking closely, it's only even to odd differences. So for example, we don't have access to C2 minus C1. The way we solve this problem is by shifting all the amplitudes right by 1, rotating the last amplitude all the way around, and then performing the entire algorithm now on the new quantum state. This is the actual matrix that allows us to get the transformation, denoted by D. Putting everything together, we are now able to obtain all pairs of adjacent differences. However, these are only in the horizontal direction, so we need to transpose the entire image and repeat the same process. This way, we can also obtain full differences between every pixel and its neighbors. Note that this is why the quantum takes O of n time, because it performs the Hadamard gate in O of 1 and the amplitude permutation O of n.
With a limited number of qubits, we could also only process certain size images. To combat this problem, we came up with 2 solutions. The first was to convert images to a lower quality before processing, but that has some downsides to it. Our second method, however, breaks the images into smaller images and processes them one at a time, and then combines them all together at the end. This allows us to use a small number of qubits and still process large images.
Another problem we faced was using absolute thresholding. After a lot of debugging, we realized that we actually need to use relative thresholding because the distribution of pixel differences can be very different across different images. So the 2 ways that we came up with doing this are k-adaptive thresholding and max-adaptive thresholding. And combining this with the rest of the algorithm, we can now obtain some pretty incredible results, as we can see in the bottom. And this is another image which worked really well.
Now, onto real-life applications. There's a variety of real-life applications edge detection can have, including remote sensing and computer vision. The images on the right are examples of QHED applied to pictures on the road. Additionally, with 80% max adaptive thresholding, tumors in the scans of the brain appear very clearly. These are results from our implementation. However, QHED struggles with compressed images and images with too much detail. The pictures on the right demonstrate this. Classical pre- and post-processing also doesn't experience a reduction in time complexity with the qubit speedup, and images must be manually resized so dimensions are divisible by the grid size as well. Plus, the value of k for thresholding must be adjusted for certain images. These are all points to improve in the future. Here's the resource estimation we had for a 2x2 grid. 3 qubits were used in one of the circuits, and the depth of the circuit was 6. There are also 2 circuits, one vertical, one horizontal for each grid. This is important to check because as depth increases, so does the probability of error, and even with this few qubits, errors appear as shown in the green box. So although the number of qubits is a log of grid size n and this can be adjusted, it's hard to avoid. On larger scales, the number of qubits will increase logarithmically and depth will consistently increase as well. If any of you are interested in something more technical, check out the link on the slides here. It's a paper with much more detailed explanations of QHED and how it works. And lastly, as per our team name, here is us with Capybaras as an Easter egg, and here are our references and our citations. Thank you very much.